All right, next we have example 2, and we are to determine the equation of the tangent line at the point 1, 1 to the given curve, which is some implicitly defined, to the curve of the graph of this equation. It's some implicitly defined curve. So let's go ahead and start. Whenever we're asked to take a derivative or find the slope of a tangent line, or the equation, we just want to take our given equation here and differentiate each side. So the derivative of y to the fourth plus xy equals the derivative of the right-hand side, which is x cubed minus x plus 2. Now remember, if we're differentiating something that's a constant or an x, it's the derivative as usual. If we have y's involved, then we have to think about when do we add on this dy dx term. So the left-hand side here, we're differentiating a y term with respect to an x, so that means we're going to need a dy dx when we differentiate this. So we're going to go ahead and differentiate as normal for y to the third, but then we have to tack on this dy dx. Plus, now we have a power rule here. So, no, excuse me, a product rule I meant to say. So if we have a product rule here, ddx of xy, I'm going to write this out a very lengthy way just so we can see what's going on here. The way I'm going to do this is I'm going to take the derivative of the first times the second left alone plus the first times the derivative of the second. So here, because this x is the only thing being differentiated in this term, we don't get a dy dx because the only derivative is on this x. So this becomes 1 times y plus x times the derivative of y with respect to x is 1. So I'll write this as times 1 dy dx. But again, we don't need to write the 1. That's kind of silly. So it really ends up being that. So don't give each of these terms, do not give each of them a dy dx. The only terms that get a dy dx is when you just finish differentiating a y term. So this term doesn't get a dy dx, but this one does. So that's a pretty common mistake that people can make, is that they will give everything in the product rule a dy dx, where really only some of those terms potentially should have a dy dx. All right, so that's the left-hand side. The right-hand side, there's no y, so this is business as usual. Now, since we have the point, we don't just want to know dy dx as an expression in terms of x's and y's, we want to know dy dx evaluated at this point. So in the previous example, in the previous video, in example 1, we went ahead and solved for dy dx. For this example, we're going to show a little shortcut we can take here. So if they want to know the derivative at a specific point, then after we've taken the derivative, so once we get to this line, we can actually go ahead and substitute in this point, and it will make solving for dy dx far, far easier. So if we go ahead and evaluate this expression up here at the given point, 1, 1, then this turns into 4 dy dx plus 1 plus dy dx equals 3 minus 1, which is 2. Subtract 1 to the other side, we get 1. We have 5 dy dx. All of that, let's get some room here. So we have dy dx equals 1/5. And then we can go ahead and write down our equation of the tangent line using point-slope form. Y minus the y-coordinate of our point equals our slope times x minus the x-coordinate of our point. So a little aside here, just to compare and contrast the differences, if we actually took this expression right here and we were to solve for dy dx first, this would actually be quite annoying. So let's see what happens here. If we want to solve for dy dx, a lot of times the algebra trips up people in this section. I think it's just there's so many symbols that it seems overwhelming, but really this is no different than what you've done in an Algebra 2 class. Basically what you want to do is get everything, find all the terms, identify the terms that have a dy dx attached to them. Keep those on one side. Send everything else to the other side. So you basically get all of your terms of a dy dx on the one side, everything that doesn't have a dy dx goes on the other side. So in this case here, let's go ahead and keep the dy dx's on this side. Okay, and then we'll send that y to the other side. So now once we've done that, since everything on the one side is guaranteed to have a dy dx, that means it's in common amongst all of those terms, so that means we can factor it out. And then we can divide by that factor. There you go. So that's actually solving for dy dx. Now that was a bit more work. And then, once we get here, if we go ahead and plug in 1, 1 here, you'll see that we do get 1/5 as well, but this was so much work compared to first plugging in. So whenever a question wants to know the derivative at a specific point, you are always free to use this nice little shortcut here. It will dramatically simplify things. But some questions, they don't want to know the derivative at a point. They just want to know what the derivative is, in which case you have to do this method of separating, so getting all of your dy dx terms to one side, sending everything else to the other side, factoring, and dividing.